Over half a century ago, astronomers discovered a strange kind of cosmic object tiny as a city, yet heavier than the Sun itself, the neutron star. These are the remnants of massive stars that died in spectacular supernova explosions. In their final moments, the cores of those stars collapsed so violently that protons and electrons were crushed together, forming densely packed neutrons. The result is a sphere only about 20 kilometers across, but weighing between 1.4 and 2.3 times the Sun's mass. A single teaspoon of neutron star matter would outweigh Mount Everest. And perhaps most astonishingly, the chemistry inside such an object completely defies everything we know on Earth. On the surface, neutron stars have a rigid crust where atomic nuclei are squeezed into bizarre shapes that physicists call nuclear pasta. Despite the name, it's not edible, but under the microscope of theory, these nuclear structures resemble spaghetti, lasagna, or gnocchi. They form when the powerful strong nuclear force and the repulsion between protons reach an odd balance under extreme pressure. Supercomputer simulations by Charles Horowitz's team published in Physical Review Letters in 2015 suggest this could be the strongest material in the universe, up to 10 billion times stronger than steel. While we can't directly see nuclear pasta, indirect evidence from gravitational wave signals and the remarkable rotational stability of pulsars strongly suggests it exists. Beneath the crust lies a realm where neutrons begin to leak out of nuclei, forming a strange quantum liquid, neutron superfluid. This is a state in which neutrons can flow forever without friction, similar to superconductivity in electrons, but on a nuclear scale. Here, the temperature is still millions of degrees Kelvin, yet cold enough for neutrons to pair up and move in perfect unison. This superfluid layer is thought to cause sudden glitches in neutron star rotation, moments when the star abruptly spins faster for a fraction of a second. The Vela pulsar has exhibited such glitches repeatedly since astronomers first observed them in 1975. Deeper still, at the very core, pressures and densities reach mind-bending extremes, tens of millions of times the pressure inside Earth's core. Under these conditions, neutrons may themselves break apart into their fundamental components, quarks, held together by gluons. Matter in this state is known as quark-gluon plasma, the same primordial soup that filled the universe just microseconds after the Big Bang. While we can't sample it directly from a neutron star, data from the 2017 neutron star collision event GW170817, detected via gravitational waves, suggest their cores are softer than models predicted, possibly due to the presence of quark matter. Laboratory experiments at the Relativistic Heavy Ion Collider RHIC in the US and the Large Hadron Collider CERN in Europe have already recreated quark-gluon plasma for tiny fractions of a second, helping scientists refine their models of what lies deep inside these stars. In such an environment, our everyday concept of chemistry collapses. Atoms, molecules, chemical bonds, none of them exist here. The periodic table is reduced to a single entry, the neutron. And at the deepest layers, even neutrons give way to free quarks. Yet, despite these alien conditions, the fundamental laws of physics, the strong force, the weak force, and quantum mechanics still govern every interaction. Studying neutron stars isn't just about satisfying curiosity. These cosmic laboratories allow us to test the most fundamental theories of matter under conditions impossible to reproduce fully on Earth. They may reveal new insights into the strong nuclear force, the force that holds atomic nuclei together, and even inspire ideas for ultra-strong materials or high-temperature superconductors. Far from being just the graveyards of dead stars, neutron stars are the most extreme testing grounds nature has to offer, where matter is pushed to its ultimate limits, challenging both our imagination and our understanding of the universe.